and made available. There we go. So this will be made available afterwards, and also we'll share the slides for this presentation afterwards. During Ken's talk, please stay on mute, and feel free to put your questions in the chat during the presentation. After the presentation, we'll have about 10 to 15 minutes for some Q&A, so you're welcome to continue to put your questions in the chat, or just unmute yourselves and ask your questions directly to Ken. And with that, I'll go ahead and introduce our speaker and we'll get started. So Dr. Kenneth Armijo is a systems engineering staff member who leads molten salt and molten alkali metals R&D at the National Solar Thermal Test Facility. His research interests are in alternative energy technologies and sustainability as they pertain to scientific and technological innovation, business, and policy. Dr. Armijo holds a PhD in mechanical engineering from the University of California, Berkeley, with minors in energy and resources and business credentials in management of technology from Berkeley's Haas School of Business. Presently, Dr. Armijo is the lead for the HelioCon components and controls task, who is co-led by Matt Mueller from NREL. His research in concentrating solar power also consists of systems designed for high temperature, thermodynamic, and commercial R&D systems employing ternary chloride molten salts and alkali metals as the heat transfer fluid. He is the test site principal investigator for multiple U.S. Department of Energy projects in CSP that also includes pumped thermal energy systems. His research has also consisted of falling particles for centralized concentrating solar receivers and solar reactors for industrial process heat applications and climate change mitigation technologies. He also leads research activities pertaining to solar Stirling energy applications, as well as for solar reactor R&D and high flux materials characterization. Dr. Armijo also serves as a lead test director for high temperature materials research for aerospace applications, such as reentry and hypersonic vehicles. All right, so thanks for giving a seminar today, Ken. Why don't you go ahead and take it away?
My pleasure. Thanks, Rebecca. So as Rebecca mentioned, I will be talking about components controls. My co-lead for this task in HelioCon is Matt Mueller. I'm just showing back here just to kind of give our, I guess, our minds in the viewpoint of heliostats as they pertain to towers. There's a lot that needs to happen in order to make heliostats put beams on accurately onto receivers and onto tower systems, and which is why we're doing all this kind of work. So for components controls, I will go ahead and see if I can advance. For this outline for today, I'll talk about the task scope, state of the art, and as well as a little bit of a tie to Gen 3, and as well as components control survey and stakeholder engagement that we've been doing, and gap analysis, where we've identified some challenges and mapped out required activities, and down selected and prioritized to our top tier components controls gaps based on the feedback from the surveys and stakeholder engagement. And also talk a little bit about codes and standards as we are developing that for heliostats, and in general, what the value of HelioCon components and controls can be for the CSP industry. So within the HelioCon, there's a task 6, components and controls, where presently we have one milestone, 1.6.1, which is looking at environmental factors and surveying components and controls challenges and gaps for the heliostat industry. As we move forward, we will be digging a little bit more into those specific gap areas and seeing how and where we can, as a HelioCon, help to improve the industry so heliostats more bankable. So for definition and scope, heliostats, we require them to have relatively high pointing accuracy with small milliradian errors and be able to facilitate accurate pointing and control over varying temperatures, as well as other environmental conditions, such as with wind loads, which another task led by Shashank will be talking about during his presentation. There's also optimized pointing from the standpoint of robust mechanical rigidity for these wind loads, especially when you're dealing with backlash. What does that mean for components controls? Well, there's drives that need to be optimally designed to withstand backlash and also be able to operate under different wind load situations and scenarios to be reliable for a 25 to 30 year lifetime. So there's optimized service life is something that we want to be able to also look at to also help reduce costs related to operation and maintenance, or O&M. And so ultimately driving towards the DOE CETO target of $50 per meter squared, there's a lot that needs to be done from different taskers, but for components controls, we're looking at the individual components and which ones have high costs in the short net present value aspect, and then also annualized costs over the life of the system. So that's primarily where we're looking in terms of bankability, in terms of our objectives. And for components specifically, we're looking at test protocols, cataloging the different types of drives, since that pertains to the highest costs traditionally in the heliostat design, as well as understanding what kind of costs also impact for subcomponents, impact levelized cost of electricity, or LCOE, or levelized cost of heat, LCOH. And then benchmarking existing measurement tools for qualifying and quantifying errors within each of these individual components. And then looking at the controls, what are the state of our open loop communication as well as closed loop communication, and seeing where the ties are from other industries and cross-cutting to closed loop control and wireless communication, which is something that is ever growing within the CSP community. And then also looking at publishing standard operating procedures, guidelines, and then of course publications. I'd like to also mention the broader team of our components controls task team. At Sandia, there's myself and Rebecca Schaller from Sandia, who works in reliability for materials. There's Matt Muller from NREL, who's traditionally been working in photovoltaics. He's worked with a lot of CPV, concentrated photovoltaics, especially as it pertains to drives. So there's a natural connection here in the heliostat components controls. And then we've also collaborated with Mike Collins and Matt Eames and Maziar from University of Adelaide as we are looking at the intersections of environmental conditions with components controls. We also have a number of interns from both NREL and Sandia as well. So getting into the state of the art for various components, I'm just going to highlight a few. Since there are many components, I'm just going to focus on, in this slide, mirrors. There's conventional designs of reflective areas. There's been work to look at glass, not just at 3 to 4 millimeter, which is typically employed, but also seeing how we can reduce the cost by going down to 1 millimeter glass, and also staying within the standard 3 to 5 degree canting, which is employed for concentrated focusing within individual facets on a heliostat. There's a lot of reliability challenges, as we've seen with mirrors, including soiling, and that's created by, that's being facilitated by another group within the HelioCon to assess soiling degradation and attenuating impacts for optical accuracy. With regards to torque tubes are utilized for axis and elevation angle control. There can be reliability challenges, especially when you consider high wind loads, as well as turbulent wind loads for different types of systems. And there's been optimization studies to see how we can also reduce the overall weight of torque tubes while still providing good, reliable rigidity and accurate, operation during wind loading events. Torque tubes can also be used to create different types of facet rows, and there's been different permutations over the last 30 years, especially looking at various designs. For pedestals, pedestals have also been looked at in order to reduce their size, in order to reduce weight and costs, especially when you're considering transportation. But they also can face reliability challenges, looking at ground penetration, depending on soils types, and figuring out how those pedestals can also be improved from a reliability perspective, while optimizing their material volume. And in some cases, also looking at how the pedestals are placed within the ground with regards to ground conduit, but then also looking at even vegetation and being able to consider its placement even deeper in the ground in some cases, where you can actually put plants, so any water runoff can also be leveraged to the plants to also reduce erosion effects at the ground base. There's been optimization studies to also look at not just diameter, but also wall thickness to optimize cost, but also look at reliability. Trusses also can vary greatly within a heliostat. There's the design of the horizontal versus vertical trusses centered on the horizontal torque tube. And there's been different permutations of the design where some have even tried to get rid of the trusses and just make a single backplane for mirrors, so you can have the reflective area and the structural area be one and the same, while providing enough rigidity to eliminate some of this added cost of a truss system. For drives, they constitute one of the, well, if not the highest cost in a heliostat system. Generally speaking, for heliostats greater than 20 meters squared, there's typically a slewing drive with linear actuators. And for large heliostats looking at reflective areas greater than 120 meters squared, hydraulic drives have been employed. But there's some instances in the literature and in discussions with different stakeholders that there can be reliability issues with regards to gaskets, fouling, if seals and gaskets are compromised. And that has an impact on O&M and then also cost of actually switching out these components. Part of the interest in drives also in terms of pointing accuracy looks at the mechanical transmission and seeing what types of gear configurations, such as worm gears, also looking at the chain gears, bracket pinion systems, and all of these that I mentioned on this third bullet, also play into the selection of drives and also looking at alternative drive designs to improve pointing while also improving rigidity and then general transmission. CFD studies have also showed how pedestal mounted drives may be at risk from damage from high wind loads, and then looking at alternative drive designs that also can be made cheaper without looking at pedestal mounted drives. In general, pedestal mounted drives are easier to implement, it seems, from literature and from some stakeholder engagement, just from a design standpoint. But there's still, of course, more interest out there looking also at tracking errors and how those can be avoided. So as I mentioned, general drives that we've seen in industry currently look at worm gear and slew drives for the azimuth rotation, where you can utilize linear actuators or even jack screws type components for elevation manipulation. There has been some interest in leveraging lower cost linear actuators versus the slew drives to also reduce costs as well. DC motors also have some level of reliability challenges when it comes to dust ingress, as well as temperature effects when you're in deserts that can go above like even 45 degrees Celsius, as well as temperature cycling effects. So there are codes and standards that can be leveraged from other industries that have to deal with high temperature and thermal cycling for electronics as something that needs to be considered here within the drive, and also trying to make everything compact and sealed. Within heliostat controls, there's different types of operational modes that an operator within a heliostat field needs to consider, such as the wake-up mode, maintenance mode, that for stowing, tracking, and then for calibration. All of these different types of operational modes, and I'm just naming a few, there are others, need to be taken into account at different points in time when you're operating a heliostat field, where some heliostats will be in one operational mode pointing onto the tower, while you're taking others off in a maintenance mode or in a mode that might need to require calibration. So in general, with movement of two-axis motorized systems, for open loop communication, you're typically provide a latitude, a longitude, time and date, time of year, time of day, and then also with respect to the coordinates of the receiver. And then based on that information, you compile a heliostat control that will allow the heliostat to relatively track a point on the receiver. The challenge with open loop communication, which we've had to deal with here at Sandia's NSTTF, is there can be a lot of error involved. And so closed loop communication is very attractive because you can get more real-time information and updates, so that way you can more accurately point your heliostats towards a tower. And so within the scheme of controls, and I'll just show this, I know this is a little bit of an eye chart, but I just wanted to kind of show the feedback mechanisms when you're looking at sun tracking. Sometimes we utilize IR cameras, and in some cases, beam characterization systems, or BCS, for calibration, and also improving the pointing accuracy of not just single heliostats, but groups of heliostats within a heliostat field for looking at the control system and seeing how that convolves towards the overall sun tracking of the whole heliostat field onto the receivers. So there's a lot of feedback that needs to be considered within the control system, and also looking in terms of the error and then operational time periods where you might need to go into calibration or O&M. And then the other aspect is also looking at weather effects, looking at how cloud transients also play into the controls, as well as the actual turbine processes for, like, if you're working with steam or charging your thermal energy storage tanks. So it's not just a function of just moving heliostats to your receiver, but also being able to control accurately your heliostats during other transients with respect to the balance of system, balance of plant, such as that from your power block, as well as other environmental effects, like I mentioned, cloud transients. Within closed loop control, which, as I mentioned, has become more and more popular versus open loop communication, where you set it and you hope that everything goes properly, you can leverage different sensors. There's this great paper by Sattler in 2020 who looked at camera targeted control systems, looked at the transmitter towers that can be placed within a heliostat field with respect to cameras that can be also leveraged for a tower, looking at groupings of heliostats. There's also been interest in leveraging drones and UAVs for looking at pointing accuracies and even individual canting errors from groupings of heliostats onto a tower. And then, of course, looking at different cameras onto different calibration panels that can be placed onto towers. Challenges that some have seen with these calibration panels is there's also temperature effects. So anything placed onto towers also needs to be able to guard against heat transients in case you have heliostats that go rogue within your communications. And within the control systems, there needs to be a lot of redundancy to make sure that communication signals you're adequately able to guard against or be able to have redundancy in case there are signal losses, and then also temperature effects of your sensors that could be potentially on towers. So these are the types of things that we're interested also in from the HelioCon to test during some of the test bed work in the future. Now, I'm going to present a few tables, and I apologize again if they're a little bit of eye charts. I will highlight some of the aspects of these as a summary of some of the state of the art. Again, drives being some of the most costly aspects of a heliostat system, but also with some of the reliability challenges as well. And with respect to drives, also looking at the developments for reducing costs is very important with respect to pointing accuracy. For structures, there's been a lot of interest in looking at composite materials, replacing some of the more costly and more weight sensitive components, especially during transportation, which adds more costs. So leveraging composites also to improve reliability is also of interest. Mirror facets, as I mentioned, typically 3 to 4 millimeter glass, 3 to 5 degree canting, and then leveraging 1 millimeter glass panels supported by a sandwich construction or a more convolved type design where you have the mirrors acting as your structural piece and your reflective piece at the same time is that very strong interest. Standards, there's a lack of standards with respect to heliostat centric. There is an IEC 62817 that I really recommend a lot of folks look at, since there is a lot of crossover between CPV and heliostats. And in a lot of ways, they're already talking about heliostats in a lot of ways, but they don't really spell it out. And so the idea behind what we like to do with codes and standards in the context of components and controls is see what standards are out there that we can be developed. And we'll talk a little bit more about that in a bit. There's also, I'll mention wireless controls that are of interest, and then also safety, resilience, and security. Cybersecurity within the control scheme is also something that's gaining more and more interest, especially as heliostats not only, unlike PV that just won't produce your great IV or your maximum power point tracking in your IV curve. Instead, you can actually create fires, start fires, and have all these other issues. So having resiliency and redundancy is important, but also guarding against cybersecurity attacks. So as part of the HelioCon components and controls, we've conducted a survey over the last few months where we've sent out emails, many to, or some to all of you all, and also gained some stakeholder feedback, such as good feedback from folks like BrightSource and others to tell us from an operator standpoint and a plant developer standpoint, what are the pain points for heliostats with respect to components and controls. And I've mentioned some right here in this table to the right, but also just going to some of these facilities, part of the HelioCon, such as Ivanpah and Ashalim. Again, thank you to BrightSource for allowing this, and understanding some of the challenges. One of the things that we've also seen an interest in is reducing some of the cost of field deployment, which my colleague Jeremy Smith has talked a lot, or has already talked about, by leveraging the topology. But with respect to that topology, also being able to create components within the manufacturing paradigm that can also just still be one size, but be able to be varied in depth, like I mentioned with the pedestals, but then also having components that can be reliable in different scenarios, such as if you're in or near a watershed or on top of a hill. And then part of this work has also been looking and identifying test beds and types of work that these test beds around the world, such as that CSIRO, Sandia, NREL, and others, could be leveraged to help provide input and testing for drives, looking at reliability challenges and also performance challenges. We facilitated initial gaps list, as you see here, but we did this initial gaps list as part of the HelioCon in the context of the different phase processes of a heliostat, from conceptual design to the heliostat field. And one of the things you'll notice throughout all of these various gaps that we lay out here, where they're numbered from C1 to C17, is that you'll see, like, for example, composites materials for heliostats in the reflective mirror, as well as the other components, such as even the truss system, could help be impactful, not just in the conceptual design, but when you're looking at the components themselves, how they integrate together as part of the integrated heliostat, and then also even in mass production. And for some, looking at coatings of mirrors, where coatings can go on multiple components, but especially on mirrors, you could see that this is a gap that is seen throughout the entire life cycle progression to the field deployment, and is a very, very important area that needs to be considered. So taking all of these various gaps, we started to look at prioritization of these gaps throughout the system. And what we also looked at with respect to the prioritization as part of this activity, we looked at addressing strategies and also what types of benefits one could have for the developments, leveraging composites, leveraging lower cost mirrors, coatings, alternative drives, flexible wired communication or wireless communications for heliostat next generation development. What we also saw was areas that maybe perhaps funding, not just from the government, but maybe funding that could be coming from industry as well, and a collective effort as part of HelioCon, could help to facilitate test beds with codes and standards developed within the HelioCon space and with bodies such as Solar PACES could help to bridge some of these gaps. And We've also been looking as part of HelioCon, what types of costs from an LCOE, LCOH, that by bridging these gaps, what kind of benefit we could have more quantitatively. So for some of the lower gaps that we also looked at from the lower tier gaps, we also saw some needs for durability standards for the glass and mirror, but also looking at safety aspects and being able to like scram or take your heliostats off in a certain way that would also not affect ancillary issues where you might have to reset your control system or have any other challenges where if your heliostats are very close together, you don't have any that had interference issues, which could cause breakage, and then more O&M downtime. And then also looking at degradation aspects, not just related to the mirrors, but also to some of the other subcomponents themselves, and what test beds and codes and standards need to be developed. And so there's much that is of interest to us, also not just from the developer, but also from the heliostat operator, and what types of consequences might occur if these types of gaps are not addressed, and maybe again providing some different strategies. So what we did was we took those various gaps in components and controls, and then like I said, we pared them down to our most important tier 1 gaps, where we saw that lowering the cost of mirror designs is very important. Composites, one that's not listed on here, but we've also moved up, is drives costs, and putting that in the component space, since drives do present one of the largest costs of heliostats. That needs to also be addressed now as a tier 1. And then with regards to the integrated heliostat wireless systems and how their flexibility needs to happen and the resiliency, again, if you get signal loss or signal attenuation, is a very important aspect. There's been research before where with wireless communication, you get reflections with the glass at different frequencies, or you don't have enough redundancy where maybe you need multiple frequencies with multiple antennas in your wireless like mesh network in order to guard against any signal loss issues. We've also looked at the field deployments in tier 1, looking at closed loop control and need for design qualification standards. For tier 2, we saw that there's alternatives are needed for drives, but we moved that to tier 1. Apologies. But also in tier 2, we looked at coatings for mirrors are needed. And I know my colleagues in the soiling groups will talk a little bit more about that. And then also design and O&M are not well coupled. That can be a challenge, particularly on the reflective areas for heliostats. And I will say that there are some companies that have done a pretty good job of trying to address these issues or having addressed those issues, but there still needs to be some work depending on scale of the heliostats. Also for tier 2, mirror quality should be adaptable to different environmental conditions. For example, here in Albuquerque, we're getting a lot of forest fires, and those smoke aspects can have a spectral impact. So it's not enough to just look at optical quality with respect to like a clear, ideal sunny day, but what happens when you have high humidity or a high amount of smoke or high dust? How does that impact the spectral quality and then also the mirror reflectance aspect? Looking at need for CSP-centric durability standards, I mentioned reliability. And then for tier 3, flexible wired communication is also of interest at these interconnections, not just in terms of the wireless signal, but the components themselves at the encoders and the other receivers and things like that. If you need to have redundancy from one cell of heliostats to another cell, or one wireless heliostat to another wireless heliostat, if you're using like a mesh network, how flexible is that for an operator to quickly change over? Safety, we mentioned already. Also automation for calibration is a very important area. We listed this as a tier 3, but it was a very close tier 2, where automation is very important since a lot of companies are also trying to reduce their costs for operations. Having reliable and resilient automation within the control scheme is very important. And again, not just for the heliostats, but the overarching control system as it pertains to the power block turbine and thermal energy storage tank systems. And then again, with that, cybersecurity is also something that is of interest. But there's also been a lot of work in the DOE Office of Electricity looking at grid reliability and also cybersecurity, where there's some aspects that we found from stakeholder engagement that there's cybersecurity elements and our research and development and lessons learned that could also be translatable over to CSP. So impact wise, just from a cost standpoint, as part of the HelioCon road mapping report, which is supposed to come out relatively imminently this summer, we have been working on, from a techno-economic analysis, looking at what levelized cost of heat and electricity you potentially could get if some of these gaps are addressed. And so right now we are looking at a very high level and a very preliminary level when we're looking at these costs. So like, for example, for composite materials, we are looking at structural materials. If we can reduce them, their weight and their volume and whatnot by 50%, we could, to get to 10, by reducing by about $10 per meter squared, we could see an LCOH reduction of about 3%. For mirrors, lower cost mirror designs, we potentially could also see an LCOH reduction of about 3.6%. So there's a lot to do with the mirror costs and designs. As I mentioned, a lot of interest is trying to get down to that 1 millimeter thickness. But again, with problem challenges is there's a trade-off. Since if you go thinner with the mirrors, you potentially get more embrittlement behavior. And so that becomes a big challenge. So with a little bit thicker mirror, you can also improve rigidity. The other aspect too is even with thicker mirrors, you do tend to get a little bit of extinction coefficients that also can have a little bit of a knockdown with regards to the reflected light that goes back up. So there's multiple positives, but there's a lot of challenge in the design. With regards to wireless communication, not having to have conduit runs in a heliostat field is very impactful to the cost and has a little bit higher LCOH cost. But again, having flexibility in the wireless control scheme, and then also being able to have redundancy and resiliency within wireless communications and good signal quality, and be able to do checks at a relatively continual period over time, just to make sure that you have confidence in your wireless signal, is very important. Closed loop control has a big area, because again, you can improve your pointing accuracy and you can facilitate automation, and automation with closed loop control, not just in the heliostat field, but also in the balance of plant, could be really big in terms of reducing LCOH. And at least that's from some of the estimations that we've done based on certain approximations. We could see a potential 11.1% reduction. And then for design, qualification and standards, looking at ways of providing better guidance and test beds and tests that can be facilitated can be important. And that includes environmental factors, not just due to wind and soiling effects, but also to temperatures and temperature cycling, where some of the locations of these heliostats can get like very high, like I said, higher than 45 C, and in some cases even maybe higher than 50 C, dare I say. But in some of those cases, you also need to look at temperature cycling effects on the electronics, and also dust and fouling effects as well, and dust ingress and fouling effects, just as we see in the PV industry with inverters, which can have marked impacts on heating, because that dust can create some thermal insulation areas for electronics and heat them up even further. We need to, if there's vents, of course, then we need to be mindful of those sorts of things. For codes and standards, like I said, we've been looking at various codes and standards as part of the HelioCon components controls work. I mentioned the IE 62817, but we've also been looking at others like 62108, looking at concentrate CPV modules, looking at design qualifications and approval types that can also be leveraged for how we look at codes and standards development for heliostats. There's also heliostat field control system, which is in a draft form for 62862-4-2 that is in development, just so that way you all put it on your radar. So there is some interest, and as part of the HelioCon, it's also just trying to kind of bring this all together and tie it together. And of course, Solar Paces, if you come to like the first day, shameless plug for Solar Paces on the first day on that Monday of the conference in late September, early October, we have task groups that also talk about guidelines for heliostats and best practices. I'm showing here on the right some of the work that we've been talking about in the context of the codes and standards development, looking at the concentrator, the tracking system, the assembly, the sun shapes, looking at all of these various boxes in the context of codes and standards and best practices. So that way we can also reduce the commissioning time, the deployment time, and the development time of different heliostats, so we can make sure that we have good confidence in what is deployed finally. As part of our path forward, we're also looking at we have a milestone 6.1, which looks at environmental factors, which we're continuously gaining more stakeholder feedback and historical data. So we're really wanting to get more historical data from plants if that is available. So that way we can understand the impacts a little bit better of environmental effects from like temperature, wind, DNI effects, cloud transients on the heliostat components and controls. And amongst, I'm sure, my colleagues in the other tasks as well. We're still analyzing this data, identification of codes and standards. I just mentioned a few, but there are some also like IEEE standards for electronics and temperature effects, where there has been in the past utilizing HALT, highly accelerated lifetime aging and acceleration factors that could be applied to these different components, electrical components, like I mentioned, encoders, for looking at reliability effects. We've also been, we submitted one survey already to gain input back, but we're also interested in producing another survey. So please stay tuned for that. But we're going to also be looking at like wireless communication, automation, and potentially also closed loop control. Mirrors and reflectors, we've looked at some guideline standards for acceleration testing. Like I mentioned, there's a soiling group that have been looking a little bit more at the soiling effects on these mirrors. And then also looking at like maturity of the field and looking at reliability. What kind of degradation and knockdown factors do we expect over time? And then for the component systems, again, going back to the codes and standards, work with IEC primarily. I'll just show this chart just briefly. There's also an interest in the context of the Gen 3, which is another program that the DOE has. We're also looking to see if there's other ways that for the next generation power plants, CSP power plants, if there's potential for within the HelioCon components and controls that we could also address some of the heliostat development progress from conceptual design to a deployed heliostat field, such as resource of past lessons learned, getting to higher strength drives that can withstand 50 miles per hour, but also do that reliably over time. And then also looking at full durability tests of heliostats, not just components, but integrated durability tests, which could also be impactful for confidence and bankability of heliostats. And then also looking at how we can make the design of specific components within the context of mass production and what challenges there might be. Again, with regards to the Boyhood-Dewhurst methodology that we consider in manufacturing, we want to see ways that tooling can also be made a little bit cheaper. Of course, I have to defer to Randy Brose, who leads that component of the HelioCon. But from the component standpoint, looking at ways that we can optimize the design for quicker throughput is also important. And for the heliostat deployed field, being able to do confident checks within calibrations and automations is also very important. So with that, I'm going to end just a few minutes earlier than I mentioned. I'm showing a little picture here of the NSTTF. And again, the Ashalim field that we just visited. And I guess, again, I'd like to thank Bright Source for the opportunity to go see Ashalim, and for my colleagues at IVMPA, also for some of the inputs that we've had at some of the other fields. I'd also like to say thank you to them as well. and some of the work I've done in the past with solar dynamics and with Heliogen. So thank you very much. And thank you overall for this opportunity.
Thanks, Ken. That was a really nice talk. So we have plenty of time for questions. So if you'd like, as I said, you can put a question in the chat, or you're welcome to go ahead and unmute yourself and ask a question.
Hello, my name is Sidney Clouston, Clouston Energy Research, LLC, and I'm fascinated by the technology and the advancements currently in progress. Thank you for a wonderful webinar, by the way. I'm active over in Africa. We'd like to use some steam reforming of methanol to hydrogen fuel, and also ethanol and other alcohols from sugar plants, fermentation, to make hydrogen fuel. Is there a way to facilitate this activity, and are we just in a research mode?
Thank you for your question, Sydney. So I guess for the context of the HelioCon, we're mostly focused on the heliostats. But you'll notice earlier, I didn't mention levelized cost of heat. So with the levelized cost of heat, we can leverage, we're looking at the heliostats from the standpoint of industrial process heat for aspects such as calcination for cement, which is like 8% of global emissions, water I guess we could say water desalination, albeit that's a lot lower temperature. And then also for like hydrogen ammonia production. But from the standpoint of methane reforming, that's still at a very R&D stage. I guess we could probably have another talk. We do have a project here at Sandia working on methane reforming. But again, in order to facilitate industrial processing for methane reforming, the heliostats, which constitute a large cost of an overall CSP plant, needs to also be reduced. So that way the methane reforming could be facilitated. So I guess in short, there is research being done, but I think it's still at a very research level for like the solar thermal reactors for methane reforming. Hope that helps.
Thank you.
Are there any other questions?
I have a question.
Yeah.
So I'm just curious to know, was there anything maybe unexpected or surprising that you learned from your survey of stakeholders regarding this topic, components and control?
Yeah, I guess there were a few different areas that I thought were particularly interesting. Matt Muller, if you're also in there, feel free to chime in. Some of the areas that I thought were of interest to me was also looking at the control schemes, that there's so many different types of closed loop control. I thought maybe there was just like a few where you put sensors up on a tower, or you might have these masks, but like the use of drones I thought was particularly interesting, where the drones can also act not just as a means of helping to facilitate some of the control schemes, but again, also for surveying heliostats and for damage. So you can leverage drones in multiple different ways and capacities for closed loop control. But the other aspect of closed loop control that I thought was interesting is how different groups are also interested in leveraging, such as like some for leveraging PV on their heliostats for producing power for the heliostat, but also leveraging it for closed loop control as well, for assessment of DNI and looking at cloud transients and leveraging co-leveraging different subcomponents within the heliostat, not just for the controls, but for other things as well. Looking at energy forecasting and also operations forecasting. So I guess for me, closed loop control was one of the big interests that I found. And then also how we leverage automation within closed loop control, I thought was also very fascinating, since there are a lot of different takes on it. And maybe that's an area for development as well.
We have a few questions popping up in the chat. Fabian asks, what do you mean by 3 to 5 degree canting, which was mentioned earlier as kind of the standard canting?
Cool. Yeah. So I'll point out, I don't know if it's my cursor. I'm not very good with Zoom, but if you could see my cursor, there's
We can, yeah.
Okay, cool.
Mhm.
So for example, there's these facets that we have on our own heliostat. These facets have a bit of a bend on the edges, about 3 to 5 degrees. And that little bit of canting helps to concentrate on an individual level each of these respective facets to combine, improve the focal quality of the beam spot on a heliostat. And so that's what I mean, at least with ours, are 3 to 5 degrees, which, as I understand, and feel free anybody to correct me, but that's a bit of a standard with regards to canting of individual facets. And I think the other question, if I can bring that up, what does Sandia plan to do regarding wireless control? So we have a group here that does wireless controls, and we've already had some discussions with folks from the University of New Mexico, such as Rini and others, about how we can look at different control networks, wireless control networks. I mentioned flexibility being one of the gaps for integrated heliostats that's important. And what what we've been discussing is how we can look at flexible wireless test beds for looking at different types of mesh networks, looking at impacts to like Zigbee platforms or protocols, I should say, for mesh networks. Also looking at not just point-to-point heliostats, but again, point to single towers, transmitting towers for groups of heliostats, and looking at redundancies within wireless communication. And also, again, being able to guard against reflection losses and signal losses altogether. So we're looking to do some upgrades with our own heliostat field as potential test beds, but not even just for potential test beds, but for our own operations. We have a lot of different customers at Sandia's NSTTF that we'd also like to implement this, not just for flexible testing, but also for general testing as well. We're also looking at other partners at other sites, both government sites that have heliostat fields, as well as commercial heliostat fields, if there's, of course, interest from stakeholders that would be willing to roll out some of these technologies at varying technology readiness levels or commercial readiness levels for testing out some of these different protocols and wireless approaches. Let's see. All right, I see another question regarding composites. Use of composite materials for structural supports was mentioned. Can you comment on the type of composites that have been considered and what type of research has been done? So right now, I'd say composite materials has been a little bit in a nascent stage. I mean, there has been work before. Maybe I shouldn't say it's nascent, but there's been interest in looking at different high temperature polymers, as well as some even resins that have been leveraged before that are lightweight and also have either a coating on it to protect it from UV degradation. Again, there are codes and standards for highly accelerated lifetime aging for 30 years to see what the UV degradation is on some of these composites so they don't get so embrittled. But there's still a lot of interest in figuring out how those composites can be developed. One of the outstanding questions with regards to composites research that needs to be done is also looking at the overall life cycle. How recyclable are these composites? One of the lessons learned we've seen from the wind energy groups that have leveraged composites is it's trying to figure out how do you recycle these wind turbine blades after they've been in operation for a while. So as we look at composites for reducing weight and cost, such as with certain polymers, composites, I'll just leave it at that for now, since there is some proprietary nature from some of the ones I've talked to from stakeholders. There's also how recyclable are they from a life cycle perspective.
Ken, I would add, this is Matt, I would add, I don't think you mentioned, there has been a lot of work on composite mirrors. So, you know, you have a honeycomb structure, it could be aluminum or whatever, and then protective back layers, but then that supports the 1 millimeter glass. So there's been a number of research studies and on that part of the heliostat, but less on the actual support structure.
That's right. Thanks, Matt. And Irini, I think I see your hand up.
Yeah, so actually it's more as an open topic for discussion that I would like to give you a little bit our feedback. So in my lab at UNM, we have tested over simulation on NS3, the Zigbee protocol as well as the LoRa protocol for a virtual deployment of heliostats. I mean, we can only do emulation, we don't have, you know, the real field, but our first initial results, and to the best of our knowledge, there is no existing heliostat field that operates over wireless. Maybe the community can correct me if I'm wrong. So the type of network that we currently emulate is practically IPv6 over low power wireless personal area networks. The reason is that you may need more connectivity in terms of scalability within the system. So maybe that's a good input that you may want to think about. And, you know, another open research problem that you very nicely pointed out is when you have, you know, when you turn in wireless communication, the security over there is a real problem. And practically what we do is that we simulate several DDoS attacks, because a DDoS attack within the heliostat field, it's not only that it can damage the controllers of the heliostats, but practically it can capture data that are private, like data captured by drones, videos, etc. So those maybe are some points that you may want to think about.
Absolutely. Thank you, Irini. Yeah, there's several groups such as BrightSource and Solar Dynamics who have deployed some wireless communications, but as you pointed out, there's always challenges with the wireless communication. I'm glad you mentioned the other protocol. Thank you. I was blanking on the other one other than Zigbee. But yeah, there's still a lot of work because this is a relatively new way of communicating. Again, the beauty of wireless is you can deploy a field a little bit quicker, a lot quicker, and you reduce a lot of the cost of conduit. But again, I think a test bed such as yours, Irini, where you can do the simulation would be really impactful. So thank you for that.
Sure, and the cost that you pointed out, I think that, you know, it's the killing factor here.
Yeah, cost is definitely a big challenge. And then also the reliability. What's the reliability of your wireless communication over time? So again, if I don't know if your test bed's capable, but yeah, those sorts of things could be important. I see Michael's hand is up.
Morning. I guess this question continues on the wireless, and maybe it's pitched between Irini and yourself. We've had a little bit of investigation into wireless in what I call small heliostat land, so well sub 20. Whereas our heliostats are 4.5, and we've worked some clients in that 10 sub-meter space. And it didn't seem impossible, but it seemed like it was a very fine balancing act between signal quality and degradation, and a real leap compared to, you know, your big heliostat land in 100 square meter. Do you have any kind of feelings in there? Because we've kind of pursued low cost or novel cabled solutions into that space to try and solve it.
Yeah, oh my gosh, we're like talking about upgrading everything to fiber optic because we're still kind of nervous about reliability of wireless systems. But yep. I mean, wireless systems have been deployed. Like at Ashaleen, they use wireless communication for their heliostats. I think the rule of thumb that I've seen, again, I'm not going to say I'm the so-called expert by no means. I know there's people on this call that are much more experts than I. But it seems to me that shorter distances of communication and very clear distances without any obstructions is key to being able to have good quality and reliable quality. When you extend that distance that you're submitting a signal, you could get a lot more losses. So point to point communication within a wireless scheme tends to be very, very good, especially when you have like a base transmitter that's in relative close proximity. That adds cost if you keep adding more transmitters as well. So there's a balancing act that you need to look at. And again, like test beds such as the prediction test beds that Arini has, I think could be very useful figuring out the sweet spot in figuring out what is the node to node scenario, or if you, and then also maybe even size of heliostats too, because you also need, if you're in a contingency scenario, you need to scram your heliostats off or take them all off. You need to make sure you have super reliable signal quality if you need to do that.
And also, the smaller the heliostat gets, the bigger the prize there, just avoiding more and more cable cost.
Absolutely.
But
I think
the safety's been number one for us. That's been our concern.
Yeah, that's very true. Also, the other aspect I mentioned just briefly, in some fields, we tend to add more heliostats so close together, you could potentially like bump each other. So being able to also communicate by your nearest neighbor in a heliostat field, so you don't run into each other, might also be important as well. So there might even be a priority hierarchy we should start considering within the control scheme of one heliostat to another with respect to the tower. Not to further complicate it, but to me, that's what I'm foreseeing. Rini, I see your hand up.
Yeah, just a quick comment on what Michael said. So regarding the signal strength, guys, there are the reconfigurable intelligent surfaces that have been recently introduced, which are extremely cheap to be deployed, and the cost itself of the reconfigurable intelligent surface it's really low. So those are practically just passive reflectors that by using the IPv6 low WPAN, practically you can reflect the signal from the original transmitter practically all over the field without practically, not really without losing energy, but with very, very low attenuation of your signal. So that's another aspect that practically the idea is that it can be deployed at the back of the heliostats in order not to block the sun practically.
Yeah, I think wireless communication also plays well to the fact that if you have smaller heliostats, you have less material that can attenuate or reflect losses too. Back at the heliostat, I think helps. But then again, if you have a lot of heliostats and you're playing the other particular shading or blocking light with regards to that. But again, I think having multiple wireless redundancy with different frequencies and antennas might also help.
All right. Well, we're at the top of the hour. So Ken, if I could have you navigate to your last couple slides here.
Yeah, sure. Let's see here.
All right. So our next seminar will be happening June 8th. So we have Parthi from NREL will be giving a talk on bottom-up analyses for 2 heliostat collectors and initial heliostat supply chain. So be sure to tune in for that. Our past seminar presentations are on the NREL YouTube channel. We've had a bit of a backlog with getting our most recent ones up there, but they should be up soon. In the meantime, you can access the slides. So I've started making the slides available on this Drive link that you can access them, and they're all there, and Ken's is up there already, so you can access his slides. And make sure and get in touch with the Heliostat Consortium email if there any other colleagues or students want to be added to this distribution list, so you receive communication about the seminar series. And then if you want to go to your very last slide, and then just a quick plug. So separate from the seminar series, we are putting on a SolTrace tutorial. So SolTrace is a ray tracing software that's open source that NREL's developed. And so we're giving a tutorial this Thursday and Friday. There will be 2 sessions. The first one will be tomorrow, which will be a beginner's overview of it. And then the second session will be a little more advanced capabilities of the software. So they're both from 11 to 12:30 Mountain Time, and you'll need to register for them, which you can through these links, and hopefully you also received a separate email. But feel free to sign up for this if you are interested in learning more about how to use SolTrace. And these will be recorded and documented, so those will be made available afterwards if you're not able to make the live trainings. All right. Well, thank you, everyone. Thanks, Ken, for a really nice talk and for a really great discussion following. And yes, thanks again, everyone, for tuning in for the seminar series.
Yes, thanks all for joining.
Thanks, Ken.
Take care.